recording. And go ahead and take it away, Gareth, whenever you're ready.
All right, thanks. Well, appreciate you guys turning up for this. Okay, so this is a talk looking about big picture, talking about Procellarum KREEP Terrane and looking for regions outside of it. But really, the talk's going to focus on Mare Crisium, which is a nice example here taken by an amateur astronomer back in 2018. And it's quite nice as well because it shows the sort of that Mare Crisium is kind of this sort of oval shape rather than your usual kind of circular basins that you see on the moon. And that's not just an effect of the photograph. That's actually real, and that we'll come back to that at the end of the talk. Okay, presentation overview. This work is a combination of funding from both an LDAP I have, exploring the volcanic history of Crisium Basin through geological mapping, and that was we just began the third year of that. And that is to produce, it's a 4-year project to produce a 1 to 1 million scale USGS map of the Crisium region. But also being an LDAP rather than a PDOT, there is a scientific component, and particularly we were using the map as a sort of a driver to look at the various volcanic assemblages that are present in this basin, which is some of these I'll talk about today. And also, this also represents work from my mini-RF team involvement, Deputy PI there. And so we're using some of the new biostatic collects, and I'll show some data from that as well. This will also be a much shorter version talk that'll be given in 2 weeks' time in Helsinki for EPSC DPS meeting. So I'll go over the motivation, big picture, some of the map details of the project we're doing, especially because, this is an LDAP, but it's largely PSI is on this. PSI is and a bit of Smithsonian contribution as well. I'll talk about radar-based mapping, which is going to be the main focus of this. And then I'm going to focus more into the eastern portion of the basin and look at the various volcanic assemblages we found as part of our mapping work. And then, I'll wrap up with what this means for the volcanic history here, new insights. Okay, so very, very large picture. What basically was the motivation that got the LDAP funded originally is that if you look at the moon, there's this asymmetry in volcanism, and there's almost 2 levels of it. The near side of the moon, which you can see up here, all these dark patches are basalt, basically from volcanic flows that happened, billions of years ago. But if you look at the far side of the moon, there's very few. So we always have this like near side, far side asymmetry, but also on the near side, if you just to concentrate on this section here, you can see my cursor, this sort of like ellipse here, that tends to have the thickest, longest duration volcanics. It also has a large diversity of both volcanic terrain constructs, but also compositions as well. It's not just basaltic, but there's also silicic volcanics there as well. And so what's causing these various degrees of asymmetry? Well, one possibility is that when samples are brought back, there's been a collection that's got creep material, which is potassium, and rare earth elements, materials that are within this part of the basaltic collection. And so if you can look at that from orbit. I mean, we've got it in the sample collection, but looking at from orbit, you can use thorium abundance. And so this map on the left shows from Lunar Prospector, the thorium abundance. You can see it's concentrated in this area where you have the highest diversity and duration of volcanics. And so the argument here is that these kind of radiogenic materials within the KREEP terrane has kept volcanism going for longer than the rest of the moon. And so that's why you got all this diversity. And then when you look outside of this, the sort of volcanic terrain there is probably the result of where you have basins, and then they've got much thinner crusts, which allows, material. It's much easier for magma ascent and eruption. And so what we sort of said is, okay, well, that's a very nice sort of model, but in that case, we'd expect all areas that are far away from the Procellarum KREEP Terrane, which is called that because it's in the Procellarum region, should be much simpler, long and shorter durations. And so we chose Mare Crisium, as this is right out of the region, and it's sort of isolated by highlands to sort of see, well, what's the diversity there? And we're not kind of arguing against this model, but at least we want to see if it's as simple as this, or there's something more complex about the volcanic history of the moon. So that's the very big picture. The other thing that's of relevance here is that the first successful CLIPS lander was in Mare Crisium on the moon, which happened earlier this year with the Blue Ghost Mission 1 from the Firefly. And so, unfortunately, there's not a lot of instrumentation on that. It's directly relevant to what we can talk about in the work we've been doing here, but it's nice to actually have an image taken from Mare Crisium. And also, it adds excitement. So the USGS map details, as I said, it's a 1 to 1 million map. This is the region here. So Mare Crisium, which is this flat plain in the middle, it's filled with basalt. That is the main focal point, but we also covering some of the basin structure around that, the various rings, and a little bit of the edge of the ejector as well. And part of the reason we want to do this, because of this volcanic sort of motivation, is there's other Mare units that are sort of suspended up here or within the sort of between the various rims of the basin, and so we want to look at those as well. We have multiple maps data sets. The most usual one for the kind of mapping in modern form of the moon is looking at the Lunar Reconnaissance Orbiter LROC, the wide angle camera data with 100 meters per pixel, and that gives you really nice image base in which to map on. And we also use other topography data as well. But such as Lola and things like that. But we also want to we've thrown in compositional information from spectral data sets such as Clementine, M-Cubed, Kaigua terrain camera and its multiband images, which gives us composition that's really helpful, sort of like breaking out the various mafic variations in there to help you map the lava flows. But we also, what we were successful in getting money for as well, funding, was to also imply radar data, which we've done in the past on a project I was involved in that Kathy White's led. So it's great. And in fact, we've actually had, the MiniRF team have had recently some meetings with the USGS because they're looking to use more radar data in their mapping because it has multiple benefits, which I'll talk about. And particularly here, we're going to look at use Arecibo based data and MiniRF radar images as well. And so this is what I want to really focus on this expert data during this talk is what the radar is contributing. Okay, so why use radar? Radar tells us a lot of great things. It tells us things like surface roughness, which includes the surface rock population, the moon, the Mare. We think of these kind of smooth plains, the astronauts walking around, but there are a lot of boulders, especially concentrated in certain areas. So this is an LROC narrow angle camera image of a volcanic cone in the Procellarum region. And so all these little sort of dark and light dots here are all these big boulders. This is 100 meters across. These boulders are huge. Obviously, that's a problem for landing and can be a hazard and affect traverses. And what's particularly great about radar is you're not just seeing those surface populations, but you can also see below the surface. That's really key here, what sort of separates us from the other data sets. And that's important because one, it can tell us things like structure of the regolith, which is a fundamental question that's been posed by a decadal survey, but also just from a landing site safety as well. If you're landing a huge human descent vehicle, it's going to distribute a lot of the surface regolith and expose a lot of rocks. And so you might think a surface is smooth, but then once the thrusters have done its work, you might be landing on this kind of sort of uneven surface. And so radar can help with that. Radar also can tell us information about some composition as well, especially the titanium content, which is really helpful for volcanics on the moon because the basalts on the moon have a much greater range of titanium content than they do on Earth. And so, in fact, actually, we typically group the sample collection based on the variable amounts of titanium they contain. So it's really helpful for mapping that. And also more recently, being able to find other features such as like track volcanic features we'll talk about today, and also distal rays injected. Like we had a recent paper from the MiniRF team looking at Tycho crater ejecta, which they found, streaking across the south pole of the moon. Why is that important? Well, it means, when the astronauts for the Artemis programs land there, if they can land on the streak, they could get a sample of melt material from Tycho, and which can be brought back to Earth for age dating. And so, by monitoring where this material is distributed can be really helpful from a sample collection point of view. So in terms of radars, as I was sort of emphasizing at it's a kind of subsurface information, which is really, what sets us apart. And so what we're also doing in this study and across the board is apply a multi-wavelength approach. So here I've got a column with this very simple model shown. This is a Mare surface. So you've got a upper surface up to sort of like meters, possibly greater than 10 meters is regolith. This is sort of fine and consolidated material with a variable rock content. And below them is this like original bedrock, which would be the original lava flow that's been broken up to form the regolith above it. And so there's multiple data sets that can say, for example, look at rocks. You can look at them in camera images, but also Diviner, which is also an LRO, uses thermal data to produce a rock abundance metric for all the surface outside the poles where the illumination makes things a bit trickier. This is a great data set for landing site safety and for looking for sample collection, that sort of thing. So that's only sensitive to rocks that are literally on the surface. If they're buried and it can't see them. Same obviously with camera data as well. But what we can do is by doing a variable wavelength of the radar. So we XC this, which is 4.2 centimeters. Sorry, sometimes I put in here these kind of old World War II designations for the different radar bands, but we have the 4.2 centimeter, 12.6, and 70 centimeter. And the difference is that they're sensitive to different size rocks based on the wavelength and also different penetration depths, with the shortest one being only like less than probably half a meter or so. Whereas P-band, in some areas, we believe can go penetrate completely through the regolith and actually interact with the what's left of the underlying flows. And so by comparing all these and also to the other data sets, such as like the Viner, we can get a better idea of what's going on in the regolith, the surface and subsurface. Okay, so the radar systems I'm using for this, so the longer wavelengths, the 70 centimeters and the 12.6 centimeter data I'll be shown were collected bistatically. What we mean by that is you transmit from one or from a transmitter somewhere, you bounce off the target, in this case it's the surface of the moon, and then you receive it at a different location. We used to use the Arecibo Observatory prior to its catastrophic failure, sadly, a few years ago. And then receive the signals back on Earth, but at Green Bay in Green Bank Telescope in West Virginia, not Green Bay. And we used to use that. And so we created like almost near or large scale coverage of the near surface of the moon at those two wavelengths. With Mini RF here on the right, Mini RF was designed as a monostatic radar system, which means it transmits and receives from the same instrument as it orbits the moon. Unfortunately, back in 2010, its transmitter failed, but nevertheless hasn't stopped us from collecting data. And so we also operate that in bistatic mode. We used to use Arecibo to get S-band data, or 12.6 centimeter. But more recently, since Arecibo's failed, we use Goldstone antenna in California to do the shorter wavelength 4.2, which I'll be doing it. And no, I'm not a Pakistan fan, but I guess it's on my mind for some reason. And with this bistatic configuration with Mini RF, it allows us to do some kind of interesting stuff. Like we can change the bistatic angle here because we're basically collecting the received radar signal from in orbit while LRO passes down. So depending on different targets, we can change this angle here. And that allows us to kind of look at things like opposition effects, which has been very, it's potential to look at volatiles, for example. But what else we shown today is we also produced some really nice SAR image strips as well. So that's the kind of thing we're looking at. Okay, so I want to look at the radar data. I said we've got three different wavelengths, but just to show you the two end members, the 70 centimeter one here of the study area, and this is the current coverage we have from Mini RF of the shorter 4.2 centimeter. And as the way Mini RF works is that it's collecting, it's receiving basically the return from the signal from Earth and making these strips which align with the orbit of LRO. And so over time, we need a while to sort of build up orbits. We've got this nice coverage over here in the eastern portion, which is important because this is where we're going to be showing a lot of the work. What you should be able to see straight away is the P-band data. There's a lot of variation in the radar backscatter. So bright areas, we've got a lot of scatter, dark areas where there's a lack of return from coming from the moon's surface in that area. So can hopefully make out some patterns there. The X-band is a little harder to see, or the 4.2 centimeter in this, because you've got different strips. The instruments aren't radiometrically calibrated so that each strip, the absolute backscatter from one strip to the other will change. The relative, it's a grid system, so the relative variations within a given scene should be the same, but you'll get brighter and darker strips as a result of that. But nevertheless, you can sort of make up these little dots and things like this, which are crater ejecta, which are very blocky, and so they appear radar bright. Okay, so what we're going to do is the first thing we wanted to do is use 70 centimeter radar based mapping. Now, there's some precedents to this. This is work I did quite a while back now, back in 2016, was to look at, in this case, Mare Imbrium, which actually is this big circle here on the moon. You can quite easily see it with the naked eye. Is to use the P-band data, which penetrates the deepest into the subsurface, to use it to sort of map out potential backscatter variations. And here we think we're tracing largely titanium content. And the reason being is the more titanium, the more it attenuates the signal, so it prevents the radar signal from penetrating all the way through the regolith and coming back to receiver. And so areas that are dark, should be high titanium, and areas that are brighter largely should be low titanium. Of course, there could be also structure within the regolith also playing effects, but this allows you to make up these nice differences across Mare and Brim and providing a new way of mapping it. And some of these maps being used as a different perspective on like looking at the various ages and stratigraphy. For example, if you've got this this high backscatter zone, you can quite clearly see it's embayed by this low backscatter zone, which gives you some idea on the timing. And it also gives you areas where you might have kapukas of one Mare surrounded by another, which if you were to land on one of these boundaries, you can collect different age rocks from that region. Another thing it allows you to do, another perspective, if we're looking at I guess, the southern portion here of Mare Imbrium, this is where you've got Copernicus, which is a young, large crater, and so it's spread its ejecta all across the lava plains here. And so in this regular image, you can see these white streaks, which is the ejecta. But if we look at the 70 centimeter radar, you can make out all these details, including these what apparent like a lobe-like fronts, which we believe are the remains of a lava flow below the regolith. And so this gives you some information about that. Okay, and then so let's have a look at the 70 centimeter base mapping from Mare Crisium. So on the left here is the image data. On the right is the 70 centimeter data. And so what I was saying before is we think we're largely controlled by titanium. And so this is the titanium map from LROC. And you can see that on the kind of eastern edge, there's definitely some correlations here. You can kind of see these boundaries mapped really nicely. But in other areas, they don't. And so that's kind of neat because it might be the fact that in some cases we might be more sensitive to titanium that can be derived from the UV characteristics that this map was produced on. Or it could mean that there's subsurface structure or something in the regolith that's like blocky material could cause brightening, even if there's high titanium, that sort of thing. And so we want to sort of look at this a bit further. And what allowed us to do is break up Mare Crisium into these multiple units. Said most of the action here is on the eastern area. We think this area here is probably due to ejecta from some young craters that's maybe increased the backscatter due to throwing sort of rocks on the surface. A lot of this involves interpretation. That's why it's really helpful to have multiple different data sets here. But we can see a lot of these pretty neat details, including this incredibly low backscatter region, which is some of the lowest we've got just from the Mare. Normally, this kind of low backscatter is associated with pyroclastic deposits. And the reason being is pyroclastics are incredibly fine grained. And so they just appear super smooth to radar. So you get very little backscatter produced from that. But that hasn't been detected by anything else. So there's an indication maybe this is some other kind of maybe mineralogy in addition to titanium, which is really attenuating the signal. And we're not sure. And there's a few other places on the moon that show this, but it's pretty neat. So that's definitely something that we're targeting with mini-RF. And then we also see these other kind of interesting features like these bright radar features and these small dark ones as well. How does this compare to other mapping attempts? Well, this is the most recent sort of mapping of the region. This wasn't a USGS product, but it came out 4 years ago, Lou et al. And Remote Sensing journal. And so what's quite nice is this, once again, it's quite a nice bit of agreement, especially between this sort of paler unit here that we have along this side. And all these blue here are ejecta material they couldn't map. So it's good to see there's some agreement. There's also some differences here, which means we might be able to tease out more stratigraphy. And in terms of the ages, they also did dating of this. Most of these Mare were found to be about 3.5, according to the authors, except for this one area here, which was young, around 2.5, which is pretty young for Mare, which is also a matter of significance and what we'll see later. Okay, so let's concentrate on these unusual bright features. This is a LROC image. This is the boundary of the bright feature in the radar data. This is where we can see an image data. And if we put on some topography as well, you can see that it's got a really interesting sort of rough rough kind of terrain here within the center of it. And based on the way it looks and its morphology, we would interpret this within the group as a possible rugged lava flow. And then not only that, but it looks like there might be a remnant cone here. And basically, the lava flow flowed out of this cone system, and in some areas deflated, but then you've got other areas which don't have much topographic signatures or roughness signatures, but they are still bright in the radar, where we might have breakouts where basically, you've just had breakouts of lava from underneath the sort of advancing termini, which then come out, and then the rest of the flow kind of deflates behind it. So that's our sort of working interpretation for this. We can look at the sort of topography here and see this kind of cone-like feature, which appears to be the source. There also appears to be levees on it as well, which is a very common feature that you see on lava flows on Earth. So it's another evidence that this is a unique lava flow feature. And then we can do the topography on the top. Now, it's kind of tricky because all these basins have been affected by tectonics post-emplacement of the lava flows, which kind of affects the local slopes. So sometimes it can seem that we have other areas. It's very rare to see kind of topographically definable lava flows on the lunar surface, but other areas where we do see them, such as Imbrium, sometimes it looks like they're going uphill, and part of that is due to the tectonic sort of subsidence and subsidence and things like that. So it makes it tricky to look at, but certainly we think this is a possible deflated flow. The other feature I want to highlight is these very small radar dark features. And when you close up on them, they're indeed these nice cone features that you see on the moon. So this one and this. In fact, I was out in Arizona earlier this year outside of Flagstaff at the Mini RF meeting in May. And so went to the San Francisco volcanic field, and this is SP cone. These are cinder cones, and you can see there's a lot of similarities in the morphologies. And basically what happens here is that the cone is formed by, there's an eruption, you have kind of exposed component, all this cinder material basically gets thrown out, and then it builds up a cone around. And in this case, you've had a breakout lava flow as well. And this one here, the source is more of a fissure. And so rather than being a point source causing a cone, it basically causes these kind of sides to it. So very similar to what we see on the moon. And after hiking around there, you can kind of look into these features. And most of these kind of cinder cones are these sort of centimeter, multi-centimeter blocks, though you do have quite a lot of boulders within this as well. And the reason I point this out is that, when you look at radar data of Earth or this area, it's very radar bright because of all this blocky material. It makes it very rough. It's kind of interesting that on the moon, these are radar dark. Now, of course, these things are old, and so you do get regolith developing, but it's weird that they're more radar dark than the surrounding mare because they should be made of this blocky material and should have plenty of material that as you have more craters, even if you've got regolith produced, there's plenty of blocky material there to be thrown back up onto the surface. So it's kind of curious that when we want to do the comparison, then looking at the shortest wavelength radar, in this case, the X band, highlights here on the cones. Hopefully you can see here, there's a dark blob here and a dark blob there. And if you can look at the comparison of the LROC data, you can see these two cones, they match up with the appearance of these cone features, showing that both at the longer 70 centimeter and the 4.2 centimeter, you're seeing a low backscatter. So they're both in agreement. But when you look at the area here that had those potential volcanic flows that were bright and the 70 centimeters, you don't see any signature at all with the X band, meaning the X band's not seeing it, and that's telling us something about what's going on in the subsurface. As a result, and yeah, there's an example comparisons between the bright feature here and the 70 centimeter data, and you can't see it in the X band. To just show that we weren't just kind of just waving our arms, just throw a couple of distributions on here. So in this one, it's the 70 centimeter data. This is the whole of Mare Crisium return. And as you can see off this distribution, the possible flows are shifted to brighter, higher backscatter, whereas the cones are shifted to lower backscatter response. And if you look at the cones also at the 12.6 centimeter, I didn't show any images of it, but that also is shifted, as is the shorter wavelength 4.2 centimeter. But when we do the same exercise, looking this time at the flows, it's only kind of shifted off in the 70 centimeter data, both the 12.6 and the 4.2. There's no real difference between those flows and the sort of background Mare as a whole. And so overall, what does this mean? Well, the fact that we only see the potential flow features in the 70 centimeter data, that suggests that there's a localized increase in blocking material that's at least, sort of at a depth of like 2 to 10 meters. The fact we don't see it in the other wavelengths means that it can't be in within the probing depth of the shorter wavelengths, and so it must be at depth. Um, this you do also get tectonic features I mentioned previously. They do appear radar bright at 70 centimeters, but these features are much wider than that, so we don't think they're anything different. And so this is actually a very rare example of a rugged and deflated lava flow on the moon. I mean, the only other good area we can see lava flows, as I said, was Imbrium. And those are like typical. What we believe of Mare flows is to be a very high, very low viscosity, flows that can extend over hundreds of kilometers, very thin sort of flows, and that's why we think the Mare is pretty much, sort of like lacks sort of definitive slow sort of structures on that. So these are kind of unusual. They're kind of rugged, much more topography signature to them. Also, the fact that we think we can see the original cones they flowed for shows the exact sources. Even the ones in Imbrium, we don't know where the source is because they've been covered up by other mare, other lava flows. So this gives us an indication of exactly where the sources are, the point sources from those cones. As for the volcanic cones, the several on the radar dark ones, they're dark at every wavelength, which means that there's an absence of rocks, not just at the surface, but going, all the way down at depth. As I said, we're showing the example on Earth. These things should be radar bright. And in fact, they're not, suggests that they're covered in pyroclastics. Because as I said previously, pyroclastics can make the very fine grained nature of them makes the surface super smooth. And so that's unusual because there are cones elsewhere on the moon. And they also tend to be not radar bright, but tend to be the same as the background mare. So it's in suggesting there is a lack of pyroclastics in those cases. So it's interesting that there's been a difference in kind of like in the eruption history here. It makes them a bit unique. And then why are these features, this red bar here, all concentrate in this one area? Well, going back to the photograph at the start, showing that the fact that Mare Crisium is this kind of oval shape rather than a typical circular. It's made people speculate that this is due to oblique impact. And so as a result, there's probably from some work that's been doing in sort of impact dynamics and things like that, that it's probably there's a shallower shelf here. And so what there might be is a concentration of faulting in this one region here associated with this oblique impact. And maybe if that faulting's there, it provides a pathway for volcanic activity to happen. Remember, this is the area which had the youngest dates on the Mare. This is also where the flows originate. And so possibly the structure here is what's allowing this longer duration. And so going back into the big picture thing, the reason we might be seeing diversity here is not kind of questioning this sort of two provinces, Procellarum KREEP Terrane, but maybe just this unusual basin structure of Crisium is allowing it to be a bit unique, despite the fact it's away from the KREEP Terrane. And I guess I'm right at the limit there. So I'll end, and thanks very much for your time.
You- Thank you very much, Gareth. Anybody have any questions? Going once.
Hey, Gareth,
Yeah.
does this mean the impact went from right to left or?
I think it's from left to right. I believe that's the going theory. I could be wrong though. I need to look more into this. We have some impacting people on our in mini RF, so they're going to be looking at that aspect of the work.
Okay.
It definitely went one way in that direction. That out. Actually, I think it's left to right. I think this is the main crater, and the fact it came in from this direction means that you get this kind of like extra depression, but it's shallower. And the initial transient crater is shallower as a result.
Okay.
I mean, there's also been speculation. There are papers that suggest that this was a pre-existing basin out here, and that this is a new basin,
Okay.
basin. But
Yeah.
I think more favorable argument is just oblique impact.
Okay.
And there's other impact, sort of not the same size as Crisium's a big one, but kind of still large scale craters that have this kind of similar, not only kind of like oval kind of shape, but also the sort of structures you see within it as well. Kind of the shallowing on the one side.
You et al. Says that the impact was from the west to the east.
Oh, great.
Low angle impact from west to east. Oh, and
Good.
also proposed in Schultz, 1996.
That's great. Well, I had a 50% chance tonight. So
Good answer.
yeah. Thanks, Megan.
Ready. Well, thank you again, Gareth, and guess we'll be seeing each other around.
Yeah, take care, man.
All right, yeah.
You guys. Bye-bye.
Bye.